All right, calculus students, today we're looking at 6.2, definite integrals. We're going to jump around a little bit, guys, in this chapter. I don't particularly like the order of the chapter, but I really want to do all of the approximation methods first, and then we'll build up to, at the end of this chapter, we're going to build up to being able to find the exact area under a curve without having to use an approximation method. Already up to this point, just to recap, we've talked about rectangular approximation methods, RAMs. We talked about left RAM, right RAM, and midpoint RAM. And those are basically using either the endpoints of your little subintervals. You make your small little intervals within your overall interval where you're wanting to find the area under the curve. You make little subintervals, and we're putting rectangles under the curve in order to approximate the area under that curve. But we haven't built up to finding that exact area, but that's where we're headed in this chapter. At the end of this chapter, we're going to talk about the biggest theorem out of all of calculus that will marry the derivative and the integral and connect them together in a way to where we can find that exact area under the curve. But we're not there just yet. But today we have to talk about definite integrals. Before we can do the next set of approximation methods, which we're going to talk about later, we're going to jump around, like I said, in this chapter a little bit. But before we do that, we have to talk about what an integral is a little bit. So here's the parts of an integral. So you have your integral sign. It's a big, almost looks like a big hook. Okay, you got a hook on either end. They're going different directions. That is a capital letter for Greek letter for summa. Okay, which if you think about it, we've done Riemann sums up to this point, rectangular approximation methods. We've added together, we've summed up the area of those rectangles. We're summing up the area under that curve to get that total area under the curve. So that's kind of why we're using that, why they use that Greek letter there. You've got A here on the bottom of this integral. That's the lower limit of integration. That's going to be basically the right endpoint of your overall interval of where we're interested to find the area. So maybe we're interested in finding the area under the curve from -2 to +5. -2 would be my lower limit of integration. +5 would be my upper limit of integration, which is the B value. You have the function that you're integrating, that is called the integrand. The integrand. And then you have a dx, a differential here, which basically tells you what variable am I integrating with respect to. I'm doing the x is the variable of integration then in this case for dx. If my function is dealing with time, maybe I'm looking at a velocity function or an acceleration function or something like that, and it deals with time, then I'll have to use dt maybe, perhaps than dx. Okay, but that's basically your variable of integration. That means that these values are x values then. That matches up with the variable of integration. All right, so this makes up the overall parts of a definite integral. Okay. All right, well, let's move on a little bit here. Let's talk about the area under a curve, and let's define that, connecting that to an integral. If y equals f of x is non-negative, and this is my least favorite word in calculus, really. Integrable. I almost want to say integratable, but integrable is the correct word there, whatever. Over a closed interval, a to b, then the area under the curve y equals f of x from a to b is, so if y equals f of x is non-negative and integrable over ab, then the area under the curve y equals f of x from a to b is, the area is equal to the integral from a to b of f of x dx. So the definite integral gives me the area under the curve. Okay, and when we learn how to later on find that exactly, okay, even though you could do it right now even with some mild hints, you could probably go through and do that right now. But if you were to do that, you'd be able to find that exact area then. All right, so let's look at an example and then we'll have some problems that we're going to do with this today. So let's say we want to evaluate the integral from -2 to 2 of the square root of 4 minus x squared dx. Let's graph that function real quickly on the calculator. I want you to do this with me, okay? I want you to graph this on your calculators as you're watching this. Let's see what that function looks like. The square root of 4 minus x squared. When you do that, you get a function that looks like this. Okay, it's going through, it starts on the x-axis from -2, it goes to +2, and it goes through the y-axis at 2. Okay, so if I kind of graph that, just a rough sketch of that real quick. What shape is that? What shape is that function, the graph of that function then? Okay, hopefully you recognize that as a semicircle. It is a semicircle. Okay, with a radius of 2. Okay, so if we graph that, we could get the idea that that's a semicircle with a radius of 2. So this function, f of x equals the square root of 4 minus x squared, is a semicircle with a radius of 2. Well, we can find the area of a semicircle because we can use the area of a circle formula and just take half of it because a semicircle is just half a circle. So what we can do, and it's centered at the origin too, by the way. We could say that kind of in, it's centered at the origin. So this is centered at the origin. So the area, so therefore, the integral from -2 to +2 of the square root of 4 minus x squared dx, just from graphing it and seeing that it's a recognizable shape, is equal to, we're going to take 1/2 times pi r squared. Okay, half of the area circle formula. So half of pi times the radius of 2 squared. And that gives you 2 pi as your answer. So that integral is equal to 2 pi. Okay, that is an exact answer actually. So we did kind of find an exact answer today for this. So I'm going to give you some problems today where you're going to graph the function. It's going to be a recognizable shape. You may have a line, and you may be finding the area underneath the line. You know, you may have, you may have a function where it's a line, And let's say you're going from x equals 1 to x equals 3. Oh, what is that region underneath the curve? You know, shade it in if you need to so you can really see it. We're going from x equals 1 to x equals 3. Let's say that that's the line, I don't know, y equals x plus 1. We want to find the integral from 1 to 3 of x plus 1 dx. For example, well, that shape right there, that's a trapezoid. Okay, so that's a trapezoid. We need to be able to find out what the lengths of the bases are. If you remember, the area formula for a trapezoid is 1/2 the height times the sum of the bases. Okay, from geometry. Okay, and I'll try to send you a list of the formulas again, or I didn't give those to you the first time, but I'll try to find a list of formulas for you this time for real. So that's going to be the height of your trapezoid is, since your trapezoid's on its side like this is like your bases right here, B1, B2. This would be the height of your trapezoid. So the height of the trapezoid in this case is 2. And to find these, I'll have to actually plug 1 into that function. Well, if I plug 1 in there, I get 2. If I plug 3 in there, I get 4. And so I actually find the area there. That 1/2 of 2 is 1, and 1 times 2 plus 4 is 6. So that integral is equal to 6. Okay. Even later on, when we learn how to find the area under the curve exactly analytically, we're doing it geometrically today. But when we learn how to do that analytically with algebra, sometimes the geometric way is actually still faster. Okay, sometimes it is faster to go and to find the area under the curve using geometry. If you can graph the function, if it's a calculator question, you can graph it. It may not be a bad idea to look at it and see if it's a recognizable region. I could easily give you linear functions where you're going to have to do a trapezoid. If it's a constant function, it might be a rectangle even. That makes it even easier. It could also be a triangle. If I start from that x-intercept right there and go over to here, I could find the area of a triangle too. Okay, if I had started back here at that point, which would be -1, if I went from -1 to 3, now it would have been a triangle. Okay, so I'm going to give you some problems where you're going to go through and you're going to find the area underneath the curve using that method there. Okay, and it's going to be a recognizable shape.